All right, before I start this, so on this, I know we're like technically, I think a class behind. So I'm going to do this class tonight, and then I'm going to do next class. I'm actually going to do the hyperbolic functions because those have a tendency to keep coming up later on. And I normally end up skipping them in Calc 2 because nobody ever knows them. But it's something nice to understand, especially because you are going to see some of those things. So we're going to do that lesson on Thursday, and then next week will be your test on Chapter 3. So Tuesday will be the review, Thursday will be the test. Okay? I'm going to attempt to have, so I'm taking tomorrow off. So I should be able to have the review test done up for Thursday. So you'll have the review test in hand on Thursday. And if I'm really ambitious tomorrow, I'll also have the answer sheet for you. So you can go through and do it. So this way, when you come in on Tuesday, you can ask specific questions and those things on that review. So while I'm going through it and stuff, so you'll at least see it beforehand. So this test is going to be more, it's going to be all derivatives. It's basically all Chapter 3. So it's going to be, here's a bunch, literally the directions are going to be find the derivative of this function. And I'm just going to give you 10 different functions to find the derivative of. So it's just a matter of having the rules written down so you can actually go back and look at them. And on that note, here's the 2 rules for finding derivatives of logarithms. So we've got, if we're doing the derivative of log and base anything of x, it's 1 over x ln of that base. So if this is 2, it'd be ln or x ln of 2. Notice, what's the difference between this one and the one over on the other side? Very good. That's exactly why. Because ln is log base e, and ln of e is 1. So that's why there's nothing down. So the derivative of ln of x is 1 over x. That's actually going to come, that rule right there is probably one of the biggest ones in integration. Because you have quite often where you're trying to find the integral of 1 over a fraction, and the base ends up coming back to be ln of that, because it's the opposite of the power rule. And if you're think about it, if I'm doing the power rule, the only way to get x to the negative first power would be x to the 0, which is a constant, which is 1, which doesn't exist. So there's actually no way to take the derivative of something and get 1 over x with the power rule. So when we're looking at integration, the power rules, there's an opposite of it, so you actually are adding something back to it. Same concept. If we have 1 over x, it's negative x to the negative 1. If we add 1, you get 0. Or you get x to the 0 power, which is 1. So it kind of disappears. So it doesn't work. So that's where the ln of x comes into play. So really important ones to remember how to do. All right. So since we've really gone through and looked at a lot of the different differentiation rules, these rules are going to include logs and ln's and the other rules combined with it. So the nice thing is as we go through, you're kind of building on it, so you're practicing all the other stuff that we already did. So we're going to do some product rule ones, quotient rule ones, chain rule ones, all built into it. So we've got y equals ln of x to the third plus 1. So how do you think we're going to go about doing this one? Yeah, so same thing we were doing before. We have a function inside of another function. So we are going to use the chain rule for this one.
So let u equal 3x.
Nope. X to the third plus 1. So u prime is 3x squared. So then I have y is ln of u. So y prime is ln of u is just 1 over u. And then don't forget u prime. So y prime is 1 over x to the third plus 1 times 3x squared. So we got 3x squared over x to the third plus 1. That's my final answer. So this is the piece. Don't forget that. Like even when you're doing like the implicit differentiation and stuff, that y prime or those things, you kind of have to keep those. Don't forget them. Because when you don't write it, you end up having a tendency to forget putting that piece in. And you'll end up losing the 3x squared, which would be bad. All right. Try this one. So remember, there's just a bunch of different ways to write derivative. Y is, we're finding the derivative of that, or this is d dx, that's also the derivative. So just different ways to them to ask that same kind of concept. All right, so what's the u for this one? Yes, so u is sine of x. So u prime is cosine of x. So then we've got, so we got ln of u. So y prime is 1 over u prime. So y prime is 1 over sine of x times cosine of x, which is cotangent of x. Yes, cosine over sine or cotangent. You want to get it as simplified as possible. Like, so yeah, in this case, going to that is probably the easiest way to go. If you left it as cosine over sine, I'm not marking it wrong. The more important thing is remembering that cotangent is cosine over sine, because there's quite often when you're going to do more complicated things that you might have to change cotangent back in to cosine over sine. So then having to go to cotangent. So. All right, try this one. Huh? You should have one fraction at the end for this one. What's the u?
U is ln x.
Yes. So then u prime is 1 over x. So then we have y equals the square root of u, which we've done a million times, is just 1 over the square root of u, or 1 over 2 square root of u. And then u prime. So y prime is 1 over 2 square root of ln of x times 1 over x. So you want to write this as 1 over 2x square root of ln of x. That's how you'd write it. What did you make your u? Any questions with those before I move on to something a little different? Well, not really. It's just using logs instead of ln's, but I'm going to show you something different with it. All right. So this is the first one we did that was not ln. So we can start for this one. This is where sometimes the rules of logarithms can come in and help you. Let's say you don't remember the rule for taking the derivative of a logarithm, but you remember ln of x is 1 over x. So is there a way for me to change this to ln's? Yeah. So I could change this. So remember, log b of x is the log of x, or actually I'm going to use ln, is ln of x over ln of b. That's the change of base rule. So this I could change to ln of 2 plus sine x over ln of 10. Now you might think, oh crap, now I have a quotient. No, because ln of 10 is a constant. So this is no different than dividing by 2. So really, you're going to take you're just going to take 1 over ln of 10, and you're really only doing the d dx of ln of 2 plus sine of x. You're just doing that derivative right there. Which also means that's actually the reason why, if you remember the log rule, when we're doing the derivative of log, you're left with ln of whatever the base is down the bottom. That's why. It's the change of base rule. Because when I'm going to do the log there, I'm just going to have ln of 10 down the bottom of whatever was left over. So let's do the log of that. Let's see how the Yankees blow this game. They're winning 4-1 right now. All right. So ln of, let's just look at that piece there. So what's going to be my u of that? Yep. So 2 plus sine of x. So u prime is just cosine of x. And now that you've gone through and done this a few times, start to look for patterns on how it's done. Remember, it's just basically 1 over x, right? So if we look at this, this is 1 over x times whatever the derivative of the thing was. So that's in that case. Or this one's 1 over u times whatever the derivative inside was. It's 1 over that times the derivative of it. So I know that it's just the f prime of x is just 1 over ln of 2 plus sine of x times cosine of x. So I'm just going to put the cosine x on top. And then don't forget our 1 over ln of 10. So I've got cosine x over ln of 10 times ln of 2 plus sine x. Nope. Don't forget this piece right there. Oh, you're right. You're right. I do have. Never mind. You're right. You're right. Oh, I had it in the other one too. I'll go edit the video later to add out my mistakes. Huh?
No, he's right. I was like, okay, because I had it written down the way you have it now.
Always question me. You never know. You never know what I'm wrong. Sometimes I do it on purpose. Sometimes I do it.
Because you didn't do it out. That's why.
Yeah, I know. I did it quickly. Yeah. And here's the one good reason to always do your work out. So now this one I used the change of base rule for. We didn't have to. We could have done it based on the log rule. So let's look at the same problem. So in this case, my u is going to be same thing, 2 plus sine of x. My u prime is cosine x. So now y prime, so y equals log 10 of u. So y prime is 1 over ln of 10 times u prime.
Yeah, I think I like doing that way. Yeah, if you want to.
Either way, it's the same thing. The reason I was showing you the change of base rule is because one of the questions that has come up a few times, and not just a few different people have asked me this, is when you're going through and looking at manipulating problems, when do you manipulate them and when do you not? So the goal is, if you're going to manipulate something, you want to manipulate it to make your life easier. All right? So in logs, we can take things and break them apart to make them easier if you remember your log rules. So the next problem that we're going to look at, we're going to do two different ways. One, we're going to do it with no log rules, and one, we're going to do it with log rules. Yeah. God, I'm so glad when I don't have a class during the day and I can actually just relax and come to class refreshed.
Are you doing the night class next semester?
Yeah. I don't know if I'm doing the night class yet. They haven't told me what class it is I'm doing yet. But I told her I can technically do whenever they need me. And I don't know if it's easier for them to fill the day classes or the night classes. So, but I told Kelly she can put me on whenever she wants. So, as soon as I know which classes I'm teaching, I will let you guys know. Like I said, I've taught Calc 2 in the spring for, God, forever. Like at least the past 6 years. So, all right. So, now let's go on to the complicated problem that you're going to find another mistake in, I guarantee. Because that just happens to be the way my day is going. All right.
I mean, the longer the problem has to be right now, the more likely it is.
Yeah, exactly. You know, so I have an excuse this time, right?
Yeah.
All right. So we're doing the derivative of this. What is going to be my u? It's going to be my u for this one.
X plus 1 over
Yep, I use that entire thing inside.
and then that's another.
And now I have to do my quotient rule for this one. All right, so let's do the quotient rule for this one. So we've got f of x is x plus 1. F prime of x is 1. G of x is the square root of x minus 2, which now technically we also have to do this the chain rule for. So it's going to be m is x minus 2, m prime is 1. So we've got 1 over 2 square root of x minus 2, I believe. I think actually just stays just like that. Yeah. Because the derivative is 1, so it's just times 1. Yes, I skipped a couple steps in there, but I know that part's right. If you'd like me to write out the few steps, I can. But the more you practice the chain rule, the better you're going to get at being able to do it without having to write the u and the u prime and all that other stuff in there. Same thing is going to happen when you do Calc 2, when you're doing u substitution. The more you practice u substitution, there's things that are called implied u substitution. You're just going to do it without even actually writing it out because it just basically is a constant number that you're going to put there. So, all right, so now I've got those two, so now I can actually do my quotient rule. So it's the derivative of the first times the second minus the derivative of the second times the first, all over the bottom squared, which is just x minus 2. All right. So, y prime. The ln of whatever's there is, it's 1 over x, right? It's 1 over whatever's in that inside the ln, correct? Okay. Since it's a fraction in there, what can I do to this fraction? It's 1 over the fraction, right? Which is basically just does what to the fraction? It just flips it over. So it's kind of. It's a reciprocal of the fraction. So like if I did 1, so I'll write it, just, and I'm going to erase it in a second. If I did this, that's what I'm doing, right? That's the same thing as saying that. Oh, I'm not done yet. Yeah, no, I'm not done yet. Because I'm going to erase this in a second and just write that, because I'm going to run out of room writing the rest of the stuff. So this is just, so we got the square root of x minus 2 over x plus 1 times this big huge mess over here. So I got square root of x minus 2 minus x plus 1 over 2 square root of x minus 2 over x minus 2. You're not leaving it like that.
Wait, if you cross multiply, can't you just cancel out square root of x minus 2 and make it x minus 2?
Here and here?
Yes.
No. Because that's not square root of x minus 2. That's, yeah. So, no. However, the big piece that we have to clean up is right up here. Let's clean that up and then kind of work with that and see then if I can cancel some stuff out. So that part up top there, if I multiply it, get a common denominator of 2 square root of x minus 2, that's going to be 2 times x minus 2 minus x plus 1 all over 2 square root of x minus 2. Because, okay, so here, that piece right there is 2 square root of x minus 2 times square root of x minus 2. Okay? So common denominator, I'm multiplying the top and bottom by the same thing. So the bottom, the common denominator is 2 square root of x minus 2. So I multiply that times that, which gives me 2x minus 2. So I can kind of clean up the top here. So I have 2x minus x is just x. Negative 4 minus 1 is negative 5 over 2 square root of x minus 2. And that's just the top. So now what do I have? Now what I have is this. So I have y prime equals square root of x minus 2 over x plus 1 times x minus 5 over 2 square root of x minus 2 x minus 2. And now I can cross off those two. So I'm left with x minus 5 over 2, x plus 1, x minus 2. And I have the right answer. All right, so remember the red is just the red. So I was just cleaning up that piece and I got it down to there. Any questions to how I got to there? Yeah. So do you understand how I got this piece? So remember, I'm going to get common denominator. So I got to multiply, that one already has it, so I just got to multiply that by the denominator. So the square root of 2, or square root of x minus 2, square root of x minus 2 cancel each other. So that's just x minus 2. And then minus x plus 1. So then
Common denominator is square root of x minus 2, right?
2 times square root of x minus 2. So then I did 2 times x, and minus x is x. 2 times negative 2 is negative 4, minus 1 is negative 5.
Oh, okay.
So that gives me that times.
Wait, why is the common denominator 2 square root of x minus 2?
Because that's on the denominator of the right part. I'm putting these two fractions together. This has a 1 underneath it, there's no fraction. So my common denominator is just with the other ones. So now you actually are going to keep taking flip. So we're keeping this and we're flipping that over. So that's how I get the x minus 5 over 2 square root of x times the x minus 2. And now, as she was asking before, I have the square root of x minus 2 over the top and the bottom, so now I can cross them off because they're the exact same. So all that's left is x minus 5, and then 2 times x plus 1 times x minus 2. The reason we had to simplify it down as much as possible is because when I do it the other direction, I want you to see that they're the same answer. And if we had left it more complicated, you're not going to see that they're the same answer, and that's going to be a problem.
Wait, this is the first method?
Yeah. Oh, yeah. Which is why remembering the log rules makes your life easier. But again, like you can do it this way. Like, huh? No. But that's the thing. It's like a lot of things in this stuff is the more rules and stuff that you know how to use, sometimes the easier you can make your life. But that means you have to remember more things. So it's a matter of if you don't remember all the extra stuff, you can still do it the other way. It might just take you longer to get there. So. All right, same problem. So now, when you have division of logs, so if we have ln of x over y, that equals ln of x minus ln of y. So I can change this 2 ln of x plus 1 minus ln of the square root of x minus 2.
It means two chain rules, but
Yes, but I'm about to make your life even easier if you remember one of the other rules. Another rule, if it's x to the m, you can bring the m down in front and make it a coefficient. Remember, square root is x to is 1/2 power. So I can change this to ln of x plus 1 minus 1/2 ln of x minus 2. So yes, I have to do a chain rule, but what's the derivative of both things inside? What's the derivative of x plus 1? Right, what's the derivative of x minus 2? Just 1. So while yes, I have to do the chain rule, I don't really even need it because it's just going to disappear anyway. So ln of x plus 1 is just 1 over x plus 1. Minus ln of x minus 2 is 1 over x minus 2, and don't forget the 1/2 in front, so times 2. Don't forget that. That's where that 2 comes from. And if we got a common denominator, which I'm going to do just because I want these two to equal the exact same thing, my common denominator is going to be x plus 1 or 2 times x minus 2. So I've got 2x minus 2 minus x plus 1, which we just did on the other side was x minus 5. So it comes out to be the exact same thing, except it's a heck of a lot easier.
what is the common denominator?
2 times x plus 1 times x minus 2.
That. Don't you define that common denominator?
Just multiply the denominators. The easiest way to find a common denominator is just to multiply the denominators. It always works. Might not always give you the least common denominator, but it'll always find a common denominator. In this case, it is the least one because there's no common pairs. One of the rules, because I'm going through and writing the syllabus for the book and everything else for Calc 2, and I'm doing like partial fractions, those things, which is in essence what we're doing here. When you do your Calc 2 and everything else, you have to go for a problem that looks like this, where it's x minus 5 over that, back to this. And the key piece is right here. Once you have this, it's 1 over something, it's always just ln of that. So it's like that one rule makes your life a lot easier. Yes? The applications of this? In all honesty, I don't do this, so it's like it's very hard for me to go, yes, this is here's a nice, great place to use this. Depending on the functions, like derivatives are just finding your slope. It's finding your rates of change. So every type of real life type of situation has formulas that can model it. Those formulas can be quite complicated, can involve logs and everything else. It just depends on what the modeling thing was. If you're looking for the rate of change in it, you're going to have to find a derivative of it. Are you ever doing this out by hand in the real world? No. A computer will do it 99% of the time for you. All right? But the reason why we do this is so you understand the background of it. So if the computer screws up, you can figure that out. Okay? Ever see the movie Hidden Figures? Great movie. If you've not seen it, check it out. It's basically about a group of mathematicians, black women, who were called computers back at NASA. And one of the things in it is very powerful because they just got this brand new IBM computer that was literally the size, probably bigger than this classroom, to do the calculations to figure out where John Glenn was going to hit the water. Well, the computer screwed up. And one of the calculators, the black woman who actually was doing it, came in and literally did all the calculations out by hand and figured out exactly where John Glenn was going to splash down. So they could go pick him up. And he couldn't deorbit and come back until they had figured that part out. Because they needed that calculation to send the boats out there. And the computer couldn't do it fast enough for him, or as accurately as for him. So that's really the reason why we go through and do all this work, is just to be able to figure out how to catch those mistakes when they happen. Like, might not get the exact answer, but you're going to get relatively close and have an understanding what that answer is. So, and if a computer screws up, they're going to normally screw up quite big because an input was wrong and it's not going to be close. And you're going to say, wait, something's off here. Let me fix it. So that's really the reason why we go through and do this type of stuff. I tell my kids all the time, it's like the mental math is important because how often you type in things into a calculator and get it wrong, like you could switch numbers. Last night, my stats class, we were doing standard deviation of a probability curves. And I did it on my calculator, I had the answer, I had everything done there. I went over to show one of the other women how to do it on their calculator, and I had reversed the 3 and the 9. And I'm like, my answer was 1 point something, she was getting 0.8. I'm like, something's wrong here. And it took a little while to figure out where the mistake was, but we knew something was wrong. And I just reversed 2 numbers, which is really easy to do when you're typing stuff into a computer. So that's the real reason we go through and do all this stuff out. The log rules and stuff, they came up from the fact before you had computers. Like, there was log tables that you had to actually look in books to figure out. Like, if you were going to look for the log of 21, for example, you're not going to find log of 21 in a book. But you could find the log of 7 and the log of 3. And knowing the log rules, okay, that's just the addition of those two. So the log tables only gave you the prime numbers, because any number you can come up with, I can break down into prime numbers. So I didn't have to write every single possible number of logs. I only had to write the logs of the prime numbers. And then you could use the rules to come up with any number you actually wanted. I wish I could find it. My roommate in college gave me a log book from like early 1900s. And it was really cool. So, well, I can't give you an exact example. Like, that's the best I can do. If you take calc-based physics, they're going to give you a lot of examples. All right. Let's look at this one. What's different about this one? It is the absolute value.
Everyone always wrote logs constantly with absolute value signs in it.
Correct. Yes. So the domain of a log, x has to be positive. It can't be negative. So why you don't always typically see it is because, like in the last problems, is because that's assumed to be known. However, if you put the absolute value signs there, that means that x can be anything. So by putting the absolute value signs there, you are now allowing all real numbers to work in this problem. Which means when we do the derivative of it, we have to account for all real numbers. Okay? So when you have an absolute value like this, we have to look at both options. So this problem actually becomes a piecewise function. So we've got ln of x when x is greater than 0. and we've got ln of negative x when x is less than 0. So what's the derivative of ln of x? It's 1 over x, right? And that's when x is greater than 0. What's the derivative of ln of negative x? Almost. So it is going to be 1 over negative x, because that's the always 1 over whatever's inside, right? What's the derivative of negative x? Negative 1. So we got to multiply this by negative 1, which equals just 1 over x. So this function is actually f prime of x equals 1 over x when x does not equal 0. Yeah. So, in essence, what we basically just proved here is that the absolute value doesn't matter. It's still just 1 over x. So, it's just that value can't equal 0, which kind of makes sense because 1 over x is 1 over 0, and that doesn't make sense. That doesn't exist to begin with. So absolute value or no absolute value, the rule still works. Huh?
Just trying to think about this. It's like x was 0, log of 0.
Nope. Log of 0 does not exist. Log of 1 is 0. That's why, if you notice when I wrote the things, it wasn't x is greater than or equal to 0. It was just x is greater than 0. Because ln of 0 doesn't exist. Your turn. No. I'm not that mean. Well, yes, I am. But. All right. So,
I feel like it's like an easier way.
okay. Could you do this out?
Yeah.
Yes.
Is it annoying? Absolutely.
Do I want to do this out? No. So yeah, you could do this out. We would have a product rule on the top. We have a quotient rule, so we're going to have to do the quotient rule. We're going to have to do the product rule on the top. We're going to have to do a couple chain rules in there. It's definitely going to be messy. All right. So there's easier ways to do some of these things. When we start to look at more complicated functions, one of the things that pretty much everything we've done, we've only looked at one side. Okay? So we're doing these problems over here, like even this one. I didn't even have an equal sign. I was just looking at that side. I didn't have an equation to be able to solve for or anything else like that. All right? Even when I was doing these. Like I had the equals, but I just worked on this side and I was done. However, we did implicit differentiation. And implicit differentiation allows us to work on both sides of the function. So if we can work on both sides of the equation, as long as we do the same thing to both sides, you are going to come out with the same answer. Okay? And that's key sometimes when you're looking at it, is being able to work with both sides. So what have we been talking about this entire class so far? Logarithms. So let's see if we can use logarithms to break this problem up and make my life easier. So if we look at this, if I take, now whenever I do logarithms, I always use ln because it's just easier. It's nicer to write than log base whatever. But you can technically do it with any actual log. So I'm going to do the ln of this side. Since I did it to that side, I also have to do it to the other side. So ln of x to the 3/4 square root of x squared plus 1 all over 3x plus 2 to the 5th.
You can turn that into negative. You know, the one that we did on
The last one?
second.
Or the second to last one? Yeah, the subtraction part?
Yeah, subtraction.
Yeah, so I can change this to ln of x to the 3/4 times square root of x squared plus 1 minus ln of 3x plus 2 to the 5th. Now I no longer have division. That's nice. What's the rule for multiplication? If division, subtraction, multiplication would be?
Add.
Right. So this is ln of x to the 3/4 plus ln of x squared plus 1 to the 1/2 minus ln of 3x plus 2 to the 5th. Running out of room. There's a 5th. I just got to rewrite it. All right. What's next? Yep, let's move the exponents down. So ln of y equals 3/4 ln of x plus 1/2 ln of x squared plus 1 minus 5 ln of 3x plus 2. All right, I think we've got it. Yeah, go ahead.
No, I think you're right.
Let's see. Yeah, I'm good. So we've broken it down as much as we possibly can. Okay? So now we do our derivatives. What's the derivative of ln of y?
No, it's big y prime over y.
Good, yeah. It's 1 over y, but we have to multiply it by y prime. So it's y, basically y prime over y. Okay, what's the derivative of x, or ln of x? Right, so we got 3 over 4x. What's the derivative of ln of x squared plus 1? Right, so let's do the bottom. So we have the 2x squared plus 1 on the bottom, and then it's the derivative of that, which is 2x. Yeah, the 2's will cancel out. I'll do that in the next step when I rewrite it. Minus, it's over 3x plus 2, And then we have 5 times 3.
Wouldn't that be way?
Yeah. Just like I'm going to cancel out the 2's in the next one, I'm going to fix the 15 in the next one too. I just didn't want to go, because then people are going to go, wait. I wanted you to make sure you saw that this piece up here is the derivative of that. I wanted you to see that that's the derivative of x squared plus 1. I wanted you to see that that was the derivative of 3x minus 2. Not that just miraculously a 15 showed up in there. Yes? Oh, okay. So we now basically have our problem done. We just got to solve for y prime, right? So really, I got to multiply by, I got to move this y over here. Correct? Okay. What is y?
You just times it by y to figure it out.
No. What in this problem, what was y? Y was the original problem, right? So y was x to the 3/4 square root of x squared plus 1 all over 3x plus 2 to the 5th. That's y. Times 3 over x plus 4 plus x over x squared plus 1 minus 15 over 3x plus 2. And that's my answer. No, we're not simplifying. I like how the book, this is literally what the book says. If we hadn't used logarithmic differentiation in example 7, we would have had to use both the quotient rule and the product rule. The resulting calculations would have been horrendous. It's like, so one of the things I'm doing when I'm writing this book, so we have a bunch of problems, and somebody has to come up with the explanations for all the problems. So what we're trying to get the writers now to do is when you write a problem, actually do it out. Because what some people were doing is they were creating problems that were cool problems. However, when you did it out, they were horrendously hard to do.
Yes.
It's like it just didn't work well. So it's like, so the person doing the explanations was writing like pages of explanations. It's like, no, let's simplify the problems down so it fits what we're trying to teach.
I mean, they were great problems for trying to reflect, I guess.
Yeah, they're great problems they fit the thing. It was just to actually solve it out. There was so much other stuff in it, like you don't need it.
No, yes.
Like this one, it's like this was a great problem. I would not have you do it out with the product and the quotient rule. You'd be here forever doing it. This is a great problem to show you why you want to use the logarithm rules. It's like one of the questions that keeps coming up is when should I do certain things? You do certain things when it's going to make your life easier. So it's like, if you can do it out without having to do those things and it's fine, great. If not, try something else to make your life easier. And using logarithms can definitely help you do that because the logarithm rules allow you to break things apart. All right, we're going to skip that one because honestly, we don't need necessarily another one of those. And we're going to do the inverse trig functions. We're almost done. We don't have a ton more to go. So it's one of those things like I say, it's like, yes, we're supposed to be here for an hour and a half or whatever else, except your brain can't function on trying to learn all this new stuff and shove it all in there and actually process it well. So
yeah, imagine doing this at 9, up to 9.
Yeah, I would never ever suggest somebody take a Calc 1 or Calc 2 class in one night a week. The stats class alone that I'm teaching on Monday nights is a pain trying to like do all the material and like not lose people halfway through it. It's tough.
the ninth class for business management, because it's the only one that kind of fits nice with my schedule.
Some classes are fine. Like, some classes just work well with that. I don't think math does, because I think because as we were saying before, math is sequential. You need time to process and learn and understand before you move on to the next thing. So like, if you're trying to build something on top of what you just taught and they haven't learned that piece yet, it's hard to be able to process that stuff. So that's why when I put sections together, I put sections together in a very specific way that I can do that without having to overwhelm certain things. So, all right, so these are the inverse trig functions. Remember, so inverse trig functions are not the same as reciprocal trig functions, although the symbols are looking very similar. So like if you see x to the negative first power, you think 1 over x. When you see sine to the negative first power, that is not 1 over sine. Okay? 1 over sine is cosecant. This is arcsine. This is taking the side and finding the angle. This is going backwards. Okay? So it's the inverse trig function, not the reciprocal trig function. Very important, very simple to make that mistake. There is, yes, we can sit here and derive them out and everything else like that. We're not going to. These are things that you're just going to have to remember. If you see this, you can plug these in. Where is it?
Oh, X.
No, they're all X's. Yeah. Yeah, they're all X's.
Yeah, what's Z mean?
Yeah, they're all X's. Going googly-eyed. I don't know. Yes. Yeah, I don't know why when they originally created inverse trig functions. It's like inverse trig functions, I think the original things was arcsine or cosine, those things.
That would help.
Yeah, it's like I don't know why they went to this notation. I'm gonna actually find out because like I've had that question. I've never like every time I never remember to go look. I'm gonna make an effort to go look tomorrow because it really doesn't like. There's certain things that make sense, like m for slope. Like okay, why do we use m and not s? Well, because slope wasn't founded in the United States, and in English it was founded in French, and it stands for mountain, which is the slope. So it kind of makes sense. It's like okay, now that makes sense why they used m for slope instead of another letter. But this one doesn't, because I know before they came up with this, they were using -1 for powers. So, and that was the reciprocal function at that point, so I'm not sure why they switched to this. So yeah, arcsine, arccosine, arctangent, that's what these are. And it screws kids up all the time in the calculators because they think it's the, like, cosecant and those, and it's not. So I will actually have to look and figure out why. All right, but these are the derivatives for the inverse trig functions. The reason why these come up in this section as compared to the other ones is notice they have a tendency to look a lot like the log functions. When you take the derivative of ln of x, you get 1 over x. So if we did the derivative of ln of the square root of 1 minus whatever, it's going to come up to be something similar to those. So you can have it. There's kind of an overlap between the two. All right, let's look at a couple of problems. These are actually going to be pretty simple because it's just really using those rules. So we've got 1 over sine of -1x. This is a great one because now we're going to have -1 to the -1. So I'm going to rewrite this problem. So we're going to move this up so we don't have the denominator. So we're going to have arc sine of x to the -1st power. Now, how are we going to do this?
Chain rule.
Yep, we have to use the chain rule. We have a function inside of a function. So u is going to be arcsine of x, so u prime, based on what we just did. You'd think, because I just put it up there, I'd have actually remembered it by now, but I didn't. 1 over the square root of, what's it, x minus 2? 1 minus x squared. So that's u prime. So y prime is 1 over u squared times u prime. Oh, negative 1 over u squared. So I have negative 1 over arc sine squared of x times square root of 1 minus x squared. All right, one more. I want to get at least 2 of the arc stuff in there. All right, take a second and try this. I'm just going to rewrite it with the arc. So it's arc secant of x squared. What's going to be, so we have to do the chain rule. What's going to be u? That's not u.
No, I'm sorry.
It's-
Squared, sorry.
Yeah, it's just the x squared. So u prime is 2x. All right, so because this is one that's really easy to screw up. What's the arc secant of u?
1 over x is square root x squared.
Right. So when this is where I was saying this is really easy to screw up. Use the u's. So it's 1 over, and then it's u squared plus, minus 1, right? Times u prime. If you did directly to the x squareds, I guarantee you're going to mess this up. Because now this is 1 over x squared, square root of x to the 4th minus 1. And actually, I can put the top, u prime up top, which is 2x. Yes, which reduces to 2 over x squared of x to the 4th minus 1. So I can almost guarantee if you didn't do the u's, you'd have had x squared there. Because you'd have wrote x squared and forgot that it was already a squared and forgot the x. Okay.
Wait,
So-
why is it 1 over u?
It's the function was 1 over x squared of x squared minus 1 for secant. So that's why it's 1 over u squared of minus 1, because we're using u, not x. And then we have to replace the u's with what they are in terms of x.
Oh, I see.
And like I said, the reason I did that is because if you put the x's there, you might have gotten x squared here, because you had that in your mind, okay, if x squared is going to go there, but you most likely would have put x squared here and not put x to go there. It's kind of like negative and a negative, like when you say it, but then when you try to write it, it's really hard to write two negative signs next to each other. It's that force of habit. So same concept there. And we're done.